Okay, we're going to go over the practice test for the midterm. So here's question one. For each part, there's a bunch of parts. Answer with the population, a sample, data, a statistic, or a parameter. So part A. To estimate the number of New Yorkers who smoke cigarettes, John surveyed 100 people. The 100 people they're clearly a very small sample of New Yorkers. They are a sample. The only other one of these that could make any sense would be population, and they're clearly not the whole population of New York. Part B. Jane determined the average salary of the 5 janitors who work for Ed's cleaning service. The 5 janitors are, okay, the 5 janitors here are the population. And the key is that it was said that they were said to be the 5 janitors, right? Not 5 of the janitors who work for Ed's or anything like that. They are the 5 janitors. It's never said that way unless it means it's the whole population. It could be the 27 skiers at some ski chalet or whatever. As long as it says it that way, you can be pretty sure it's the population. Another way populations are indicated is to say all of something, right? Jane surveyed all the people in her class. Well, then that's the whole population, provided that her class is the whole population of interest, of course. All right, part C. Jane determined the salaries of the 5 janitors who work for Ed's cleaning service. They are, given here obviously, the 5 numbers are, well, they are just what she wrote down about each of the 5 janitors. So they are her data. Part D. For a month, Jesse identified every insect he could catch in his apartment. He found that 18% were spiders. The 18% is, well, it's either a statistic or a parameter, depending on whether you think he caught every single bug. If you think he caught every bug, it'd be a parameter, a number that characterizes the population. If you think he didn't catch every bug, which is what I would say, you would say it's a statistic. If you said population, that'd be okay if you could argue for it. Last part here. Jane determined the marital status of the 5 janitors who work for Ed's cleaning service. She found that 3 were married, 1 was divorced, and 1 was widowed. What are these results? Well, all they are is, again, just like the salaries, data written down, something written down about each one of the janitors involved. So this, again, is just data. All right, here's another one. Indicate whether the data described is discrete or continuous. Remember how to tell what this is? Right? You think of, there's going to be a data set described somehow, and you have to think of all the possible numbers that could be being described, all the ones that fit the description. And then you should think of plotting them on a number line. If they turn out to be separate individual dots with space between them, then that would be a discrete data set. If they turn out to be some interval, all the real numbers between 2 points, well, from anywhere to either infinity or both, then that's continuous. Okay, the size of a painting in square inches. What could it be? Well, I don't know if 0 is a possible size for a painting, but let's say there's a smallest size, right? It's that big. There's some tiny painting. And then from that point on, it can be any size at all, right? Whatever, this is in square inches. It could be, it could be 1 square inch, but it could also be 1.0073 square inches, or any number of square inches at all, as long as it's greater than that minimum. So this is continuous. Capacity of a car's gas tank. Well, here the units aren't given, but it doesn't make any difference. You can measure it in liters or gallons or whatever you like. And again, there's going to be some smallest possible gas tank. I don't know what it is, right? But we'll put it right there. Right? Maybe it's the gas tank for some little gas-powered drone. It's a tiny number. And then there would be a 1-gallon tank maybe, and a 2-gallon and a 3-gallon. But there could also be any other number beyond the minimum. So again, this is going to be continuous. What about the number of angels that can sit on the head of a pin? Well, however you determine it, you can have 0 angels, and you can have 1 angel, or 2, or 3, or whatever. But it's hard to see how you could have, say, 2.5 angels. Right? If you plotted the possible numbers of angels that can sit on the head of a pin, you would only get the integers, no angels, or 1 angel, or 2 angels, or whatever. Right? So this is going to be a discrete data set. How about the number of raindrops that fall on Virginia in 1 year? Well, there are lots of different sizes of raindrops, but each one is just a drop. It doesn't make sense to me to talk about 1.5 raindrops falling, for example, or pi/6 raindrops. It's only no raindrops, 1 raindrop, 2 raindrops, and so on. So again, this is going to be discrete. How about the amount of rain that falls on Virginia in 1 year in cubic centimeters? Well, that should be considered continuous. It's possible that there's no rain, 0 cubic centimeters of rainfall. That would be nice, wouldn't it? And then it's possible that 1 does, and 2 does, and so on. But it's also possible that any other number of cubic centimeters of rain falls from 0 on up. Right? So this one, again, is continuous. Okay, 3. Which of the following are measures of central tendency, and which are measures of dispersion? The measures of central tendency we have are just the 3 M's, the mean, the median, and the mode. The measures of dispersion we have are range, variance, standard deviation, and IQR, interquartile range. But here, mean, median, and mode are central tendency. Those are the only ones we have. So this is central tendency, this is central tendency, and the others just have to be dispersion, which is also called spread or variability. Right? So these guys are for dispersion. Okay. Number 4, we're given a bunch of data here, and we're supposed to do some things with it. Right? And one of the things we're supposed to do, the first thing we're supposed to do, is to find its mean. Of course, the way we would actually go about doing that would be to put these numbers, these 6 numbers, in list L1 in our calculator, and then just go to one-var stats and look where it says X bar, and you'll see it says X bar is, well, it's going to be approximately 16.5. It'll say equals a whole bunch of things, but it'll be just about 16.5. Find the median. All you do is that same display on the TI, you just arrow down to where you see the 5-number summary. One of those is labeled MED, like this, right? And it'll say 18.9 in this case. Construct the 5-number summary. Well, while you're there getting the median, you can get the whole 5-number summary. I'm not doing this because there's already a video of it in the book, right? But I'll write out what this 5-number summary is, because we're going to need it again in a second. It's 0.19, 15.27, 18.9, 22.1, 23.64. Remember what these are. This is the minimum. Over here you have the maximum. And this is Q1. This is Q3. And in the middle you have Q2, or whatever you like to call the median. What we're supposed to do next is to construct a box and whisker plot. Remember what you have to do. Draw a number line. And the number line's going to have to contain these numbers, so it should stretch from 0.19 to 23.64. I'm just going to start mine at 0 and end it at 25, let's say. And now I'm not great at this, but let's see if I can get this about right. All right, so just to get some points in there. If I wanted a real picture, I'd use a computer, so it's fine for this sketch to be not perfect. All right, and now I have to make dots where these numbers are. So 0.19, that'll be like right there for the minimum. 15.27 will be something like there. 18.9, 22.1, and 23.64. And now the box and whisker plot just looks like, you know, a box with whiskers. There you go. And this, you would probably want to label these 0.19, 15.27, and so on. I won't bother here. But that's a perfectly good sketch of a box and whisker plot. Okay, does 0.19 seem to be an outlier? Well, it sure looks like it to me. We don't have any numerical measures of this, but it certainly seems to be far away from the rest of the data. Right? 50% of the data is in here, of course, between Q1 and Q3. There could be other values out here, but actually when you look at the data, you can see there really aren't. Very little out there. So, yes, I would say yes, it does seem to be an outlier. It might not be, of course. Right? When you go back and look at your data, it might turn out to be a perfectly good data point, but it is something you ought to check if you see something that far away. If it is an outlier, which measure of central tendency should be used to represent the data? Let me remind you of the rules. If your data involves categorical data, qualitative data, then you have to use the mode, because the mean and the median don't work for categorical or qualitative data. Right? You cannot use them at all because they require calculation. If there's an outlier, or maybe two outliers, right, you should use the median. And if there aren't any outliers, well, that is in all other circumstances, you should use the mean. And so here, we've said 0.19 is an outlier, so you should use the median. Right? It would certainly be the only outlier. All right, assume that the data shows the amount of rain in millimeters for 6 different Sundays in 2009, and that you are interested in the rainfall for that entire year. Compute the standard deviation. Well, computing the standard deviation, actually getting a number, is no problem. You've still got the 5-number summary showing in your calculator. Arrow back up and get the standard deviation. Your problem is going to be that your calculator will show 2 standard deviations. It'll show, this is for the sample standard deviation, what we call S, right? And this will be for the population standard deviation, what we call sigma. Your calculator calls them SX and sigma X. It'll show 2 different numbers there. Which one should you use? And the reason for all of this, all these words here, all this explanation, is so that you can choose. The data we have here is said to be the amount of rain for 6 different Sundays, and you are interested in the rainfall for the entire year. So computing the standard deviation from that data is computing sample standard deviation, because that's clearly a sample, 6 Sundays out of 52. All right. Number 5. Jim has observed the models of Canon cameras carried by 42 tourists and compiled the following table, and you can see it there. The model variable, we have the model is a variable with various possible values, and then there are frequencies of those. The model variable is which one of these? Quantitative? It's not even made up of numbers. It can't be quantitative. Right? Qualitative? Yes, it looks qualitative. It's got values like power shot 320 HS and so on. Right? So it's definitely qualitative. Could it be these others? Ordinal? Well, we haven't learned about ordinal, but if you happen to know about it, you know that it's not ordinal data. And rational, that's not really even a good word for this. So qualitative is the answer. Okay, number 6. Janet has found that the mean of her data is 101.3. I'm going to call that, oops, no, I'm not. I'm going to call it mu, 101.3. And the standard deviation, which I'm going to call sigma, is 14.7. X bar and S might be more appropriate if this is sample data, but I'm going to call it these. Okay, what's the z-score of the data value 117? Remember how you find a z-score? Okay. Z is x minus mu over sigma, or x minus x bar over S if you have sample mean and standard deviation. In this case, this is 117, the x value, minus the mean we were given, 101.3, All of that divided by the standard deviation, 14.7. And let's see, I happen to have that written down somewhere. That turns out to be very close to 1.07. You just do the division. Excuse me. All right, what about the second half of this? What data point corresponds to the z-score minus 1.45? Well, this one is done with the same formula. In this case, we knew what x, mu, and sigma were, and we had to calculate z. In this case, we'll know what z is, and we have to calculate x. So we're going to use the same formula, only we're going to have minus 1.45. The z-score there is equal to some x value minus 101.3 over 14.7. And then you just solve for x. You multiply through by 14.7 and so on. And it turns out, what does it turn out? It turns out that x is 79.985. All right. Number 7. The Grand Island, Nebraska School District administered the Iowa Test of Basic Skills to 4,696 students in 2007. Janelle's daughter's score put her in the 63rd percentile. First, does this mean that the girl got about 63% of the questions right? It does not mean that. It's pretty much a setup, so you could tell the answer is no here. And that's all we're going to say. No, it does not mean that. What does it mean? Well, remember what the percentile tells you. It tells you where you stand, what your ranking is in the data set. So if we were to put all the scores from that test on a number line, right, maybe the scores would kind of look like this. Right? If we were to count up 4,696 scores, of course, obviously I haven't made that many marks, but if you were to count up from here, the first, the second, the third score, and so on, right, 63% of the scores would be lower than Janelle's daughter's score. That's what it means. It means if you rank the scores from bottom to top, she was 63% of the way up the list. Okay, let me add something to this. Suppose you were asked about how many students, okay, part C, about how many, let's just talk about scores, about how many scores were lower than Janelle's daughter's score. Well, 63% of the scores were lower than Janelle's daughter's score, so it would be 63% of 4,696, which is 0.63 times 4,696. And actually, I don't have that at hand. I'll get it in a second. It's about 2,958.48. That's 2,958.48. So we can say that at least 2,958 scores. Right around, let's say, 2,958 scores were lower than Janelle's daughter's score. Okay, problem 8. Find the mean of the following frequency distribution. Okay, don't get in a rush when you see something like this. Remember what this table means. Right? Students who mess this kind of problem up generally do so from just being in a hurry. Remember what this means. We have data value and frequency. The data value 4, the frequency is 7. What does that mean? That means we have 7 4s in this data set. I could actually write this out. If I wrote this data set out, that would be one way to do it. I would have to start by writing 7 4s. And then I would have to write 4 5s. And so on. Right? There'd be a whole lot of them. How many things would I be writing out altogether? Well, there are 7 4s, 4 5s, and so on. So if I add up these frequencies here, I'm going to get the total number of data points. So let's see, this is 11, 17, 20, looks like 25 altogether. Sorry. Okay, now to find the mean, what would I do? I would add up all these numbers and divide by 25, the total number of points in the data set. When I add all these up, what am I going to have? I'm going to have 7 4s, 4 times 5, and so on. In other words, I'm going to have these products. So the easiest way to do this is to just add a column here for value times frequency. 4 times 7 is 28, then 20, 36, 21, 40. The sum of all the data values then is the sum of this column, and the sum of that column happens to be 145. So the mean here is 145 over 25, which is 5.8. All right. Number 9. Decide whether each of the distributions shown is closest to a uniform, symmetric, bimodal, skewed left, or skewed right distribution. Let's see, I'm going to approach this by doing the easy ones first. I think this one is pretty much the closest to symmetric. Right? If I made a histogram, it would have high bars in the middle, and they would kind of fade away at approximately the same rate in both directions. So I'm going to say that this one is symmetric. It's got to be closer to that than any of these others. Looks to me like this one's bimodal. Again, if I made a histogram, there would be high bars, a section with almost nothing, and then high bars again. So I'm going to say this one is bimodal. Not sure about that one. How about this one? Oh, this one's pretty clear. There's very little data on the left and a whole lot of data on the right. So this is skewed left. Of the possible descriptions given here, certainly that's the best one for this. This one doesn't seem to match any of them particularly well, but it seems to me to be closest to uniform. So that's what I'm going to choose for that one. All right. Number 10. Jerry measured the actual amount of soda in 241 12-ounce bottles and constructed the following relative frequency histogram. Right, so let's see what this shows. It shows amounts of soda along the bottom in ounces, and this is, the amount of soda in 12-ounce bottles actually varies somewhat, really, in real life. Usually it's right around 12 ounces, but there are bottles in which it's a little different. So this shows the number of, the percentage of bottles that have between 11.6 and 11.7 ounces, 11.7 to 11.8, and so on. All right, what are we supposed to do here? Construct the frequency histogram for Jerry's data. And it says here that we will have to make estimates. All right, so first of all, we know that the frequency histogram is going to look just like the original histogram. It's going to have the same shape. It's also going to have the same classes along the bottom. So let's see, that's 8 classes. So again, I'm going to try to make this look reasonable. Okay, there are 8 classes. I'm not going to label all of these. 11.6 to 11.7, 11.7 to 11.8, and so on. And this is going to be the amount of soda, again in ounces, exactly the same on the x-axis as the relative frequency histogram. The difference is in what's on the y-axis, right? This is not going to be the percentage of bottles as it is up here. It's going to be the number of bottles. The actual frequencies as opposed to the relative frequencies. Well, how am I going to get the actual frequencies? Well, look at this first category. It looks like about 2% of the bottles are in this first category. And we are told that there are 241 bottles altogether. So the number of bottles in this category, right? So let's just write this out. Number in 11.6 to 11.7 is going to be about 2% of 241. 2% of 241, it's 4.82, but you can't have 4.82 frequency of 4.82. You're going to have to round this to an integer, a whole number of bottles. And so we're going to round to 5. We're going to say there are 5 bottles in this category. Right? And if you go along and you do all of these, right, for the second category, you get, I've got them written out here, 10, and then 24, and then 84, and then 82, 19, 12, and 5. I've just calculated by trying to guess the percent. I think that was 8%. That's clearly, 4%. This is clearly 10%. 35, I figured that at 34%, and so on, and doing the same kind of calculation as I did for this first one. So let's see, what does the y-axis have to look like? It looks like the numbers have to go from 0 to 84 is the largest, so let me put 80 here because I can guess better if I do that about heights. This would make this 40, 60, 20, and we'll just start putting these in. So the first category here, the one that has 2% of the bottles, that'd be about 5 bottles. So that'd be about right there. The next one would have 10 bottles. Obviously, again, just a rude sketch. Next one would have 24, somewhere like there. And then 84. Oh, it's fun to watch me do this, isn't it? Yeah. And then 82 should be just a teeny bit lower. And 19. Again, just kind of guessing here. 12. Let's see. 12. And then again, 5. Right? So there's the frequency histogram made from the relative frequency histogram. Okay, number 11. The table below shows the number of sheep with each marking color. Sorry, I'm trying to get this to focus. Good. With each marking color that Siobhan noticed on a hill yesterday. If you've ever been in Ireland and you look out at the fields there, you can see that the sheep are all dyed with various colors. Just little patches on their butts. Okay, so what are we given? Colors or no color, and then number. What is the mode of this data? The mode is the category or data value that has the highest frequency. Right? Clearly that's going to occur right here. But you can see, right, that both of these, pink and 56, are listed as answers, and that will nearly always be the case if you have multiple choice. It's the category, not the frequency. The answer here is pink, not 56. Okay. A TI calculator was used to compute summary statistics for a particular data set with the results you can see here. What's the range of the data? Well, the range is just the max minus the min. In this case, 1.362 minus 0.851. And that is, well, something. I'll tell you in a second. 0.511. What is the interquartile range of the data? You know, the IQR is just Q3 minus Q1, and those are given explicitly here. So it's 1.07 minus 0.899, which is 0.171. All right. It's one of these GPA problems. Last semester, Jackson got a C in English. Well, you know, when I'm going to do a GPA problem, I already know how I'm going to start. I'm going to have a table. I'm going to put class and grade, and then the grade value on that 0 to 4 scale, and then number of credits. Right? I've done this enough times now that I remember. And then I'm going to want value times credits. I already know this. They're done the same way every time. So let's see here. A C in English, so that means he had an English class. I got a C. A B in snorkeling. I don't know the proper abbreviation for snorkeling. A B in psych. A C in biology. And a D in French. Grade values, that's just on the 0 to 4 scale. C is worth 2, B is worth 3, 3, 2, 1. Number of credits, well, I got to read the problem for that. Snorkeling was a 1 credit class. Biology was a 4 credit class. All the others were 3 credit classes. Right? What was the GPA to the nearest 100th? All right. So what I want to do is I want to multiply the grade value times the credits in each row. I'm going to add those up, and then I'm going to divide by the sum of the credits. Right? What's the sum of the credits? Might as well get that right now. 4, 7, 11, 15. Did I do that right? 7, 10. I didn't. It's 14. Okay. Value times credits. Let's see if I can do this right. 2 times 3 is 6. 3, 9, 8, 3. Okay, so I need to sum those guys up. That's 9 and 9 is 18, 26, 29. So the GPA here is 29 out of 14. And wait a second, I happen to have that. It's just about 2.07 to the nearest hundredth. Okay. Number 14, complete the following table. So we're given some intervals, we're given the frequency of each of those, and we have to compute the relative frequency and the cumulative frequency. How do you compute the relative frequency? What's the relative frequency of this interval, for example? Well, it's the frequency of that interval divided by the total number of data points. So we're going to need the total number of data points, which means adding up the frequencies. So 10, 14, 23, 30. Right? The sum of the frequencies is 30. So for this interval, the relative frequency is 10 over 30. I'm going to write that out to 3 decimal places, let's say. Right? 0.333. For the next one, it's 0 over 30, so of course that's just 0. 4 over 30, which is about 0.133, 9 over 30 is 0.3, and then this one is about 0.233. Okay? Relative frequencies. Cumulative frequency. Remember how to get that. Essentially, we're going to go down row by row. We're going to go down this table row by row, and we're going to stop at the bottom of each row and count up how many data points we've come to so far. And that is going to be the cumulative frequency, nothing more to it than that. So in the first interval, we have 10 data points. The cumulative frequency is 10. In the second interval, we get 0 more, so that's 10 still. Right? When we get to the bottom of this second interval, we've still counted only 10. Next one, we count 4 more, so that makes it 14, and then 23, and then 30. And of course, those two numbers had better match. All right. Jan asked a number of people to estimate the average number of steps they took each day. And this table summarizes their responses. What are the questions? If a histogram were made from this table, what shape would it have? Well, it's pretty clear. Right? There's a whole lot of data on the left-hand side and not much on the right-hand side. Right? It would look a lot like this. Let's see, does it fall consistently? Not quite. That's what the histogram would look like. Right? 36 here, a couple of 32s and so on. There'd be 2 whole bars of empty, with nothing in them, and then 1 bar with just one thing in it. One category with just one thing in it. So this is called skewed right. Correct? Make sure you get those right. skewed right. Would it show a possible outlier? Yes, since there are two empty categories here, two bar widths of empty space with no data between the bulk of the data and this one value, you'd say that that is a possible outlier. Is it necessarily an outlier? Of course not. You have to examine it, though, and find out. It's suspicious. Okay, number 16. What is the mode of the data set represented by the histogram below? Well, this data set has two categories, right? These are the frequencies here, of course. Looks like it has two categories, orange and blue, that have the same frequency, the highest frequency, higher than any of the others. Okay? So this data is bimodal, and the mode is orange and blue. You report both of those highest frequency data values or categories. All right. 17. The standard deviation of a certain data set is 176.89. To the nearest hundredth, what is the variance of the data? Well, you remember that the standard deviation is the square root of the variance. So if you had the variance, you could get the standard deviation by taking the square root. Also, if you have the standard deviation, you can get the variance by squaring it. So if sigma, let's say, is 176.89, then sigma squared, the variance, is 176.89 squared, and that turns out to be 31,290.0721. All right. 18. What value of C makes the table below a probability distribution? Well, we need all of these values to be non-negative, and we need them to add up to 1, right? Because the sum of the probabilities of all the outcomes in the sample space has to add up to 1. And so this is just C here is going to be 1 minus the sum of all these others. So what's the sum of all these others? 0.25, 0.29, 0.42. Looks like it's 1 minus 0.42, so it's 0.58. Okay, 19. A bag contains several lipsticks which are indistinguishable except for color. There are 3 lipsticks of the ballerina shoes color, 2 of the blushing berry color, 1 Brazil nut, and 3 I Pink You're Cute. And yeah, I got those from a real set of lipsticks. If a lipstick is drawn at random from the bag, what is the probability that it's named after a fruit or a nut? Well, the probability here is just going to be the empirical probability. It's going to be the number that are named after a fruit or nut divided by the total number of lipsticks in the bag. So let's see the total number of lipsticks. 3 plus 2 is 5, 6, and 3, 9. And then how many are named after a fruit or a nut? 2 blushing berries and 1 Brazil nut. Looks like 3 out of 9. 1/3 is the probability you're after here. All right. Joan asked a sample of students at her college to identify their favorite pizza toppings and found the following. You can see what it is. If one of the people interviewed is selected at random, what's the probability that the person's favorite topping is pepperoni? This is just like the previous problem. It's going to be the number who favor pepperoni divided by the total number of observations. Total numbers of observations here, 63. And there are 25 who preferred pepperoni, so it's just 25 63rds. All right. Number 21. A single card is drawn from a standard deck, and a single die is rolled once. Let E be the event that the card is an ace, F the event that the card is a heart, and G the event that the die shows a number less than 3. So that would be a 1 or a 2. Find these probabilities and so on. Okay. What's the probability of E, first of all? E is, card is an ace, so the probability you draw an ace. There are 4 aces out of the 52 cards in the deck, so this is 4 52nds, right? Same as 1/13th, and that's going to be easier to compute with later on, so I'm going to leave it there. What's the probability of F? F is the event that the card is a heart. There are 13 hearts out of 52, so the probability is 13 52nds, or 1/4. Probability of G. G is the event that you get a number less than 3. The probability is there are just 2 numbers less than 3 on the die, divided by the total number of outcomes, 6, so that's 1/3. Okay, what is the probability that both E and G occur? So we're looking for the probability of E and G. That is the probability of E intersect G. Right? Well, this is easiest to compute, certainly, if E and G are independent. Are they? E is, you get an ace by drawing from the deck, and G is, you get a number less than 3 by rolling the die. It seems to me very clear that what happens when you draw the card and what happens when you roll the die are independent events. Right? So we can compute this simply by multiplying the probability of E times the probability of G. Right? So this is 1/13th times 1/3, or 1/39th. Okay. Number 22. 2 dice are rolled, 1 red and 1 green. Define these events. E is the event you get a 2 on the red. F is get an even number on the red, sum of 5, sum of 2, and so on. List all the pairs of mutually exclusive events. So what I'm going to do, I'm going to list all the pairs of events and then decide which ones are mutually exclusive. And that way I can't mess up by leaving anything out. And so there's E with F, G, and H. I could have F and G, or F and H, or I could have G and H. You may think of pairs like G and E, but that's the same thing as E and G, so I don't need to list it separately. All right, E and F, are they mutually exclusive? What does mutually exclusive mean? It means no outcomes in common. Right? There is no outcome that can make both events happen. So you roll the dice, and if the 2 events are mutually exclusive, means there's nothing that could come up that would make them both occur. So E is get a 2 on the red, and F is get an even number on the red. Right? Clearly those are not mutually exclusive. The roll 2-2 would make them both happen. Right? You get a 2 on the red, and you get an even number on the red. So those are not mutually exclusive. How about E and G? 2 on the red, sum of 5. Nope, a roll of 2-3 would do that. I'm putting the red die first here, obviously. Right? So those are not mutually exclusive. If there's even one outcome that could make them both happen, they are not mutually exclusive. How about E and H? 2 on the red and a sum of 2. Oh, those are mutually exclusive. If you get a 2 on the red, you can't end up with a sum of 2 because there's no 0 on the green, right? And if you get a sum of 2, you couldn't have gotten a 2 on the red, so those are mutually exclusive. How about F and G? Even number on the red, a sum of 5. Oh, that will do for that too, so those are not mutually exclusive. F and H, even on the red, and a sum of 2. Oh, even on the red and a sum of 2. Oh, you can't have that, right? Because you need 1-1. That's the only way you can get a sum of 2. And how about G of H? Sum of 5 and a sum of 2. Clearly, those can't both happen. So the 3 circled ones here are the pairs of mutually exclusive events. Okay, 23. In how many ways can the 40 members of a 4-H club select a president, a vice president, a secretary, and a treasurer, assuming that no one can hold more than one office at a time? Well, a couple of ways you could think about this. Probably the simplest way is to think of actually choosing them in sequence. So you're going to choose a president, a vice president, a secretary, and a treasurer. And note that order matters. If you choose Alice and then Bob and then Carol and then Dave to fill these slots in that order, you get something different than if you choose Bob and then Carol and then Dave and then Alice, right? So the order is going to matter here. When you go to choose a president, There are 40 members, presuming everyone can be elected president. There are 40 choices to be president. But that person cannot hold any of the other offices. So he's, so to speak, used up, right? Or she. So when you go to choose the vice president, you have only 39 choices, and then 38, and then 37 finally for the treasurer. And then you would just simply multiply those together. So it would be 40 times 39 times 38 times 37. And that turns out to be 2,193,360. Not that it matters very much. Okay. In how many ways can a person choose 3 movies to watch in a theater playing 11 different movies? Well, in this case, it doesn't seem that order matters. Choosing the 3 movies is all that matters, which 3 you choose, not the order in which you choose them. So it looks to me like it's going to be combinations. C of 11, 3. Or if you prefer this notation, 11C3. That's the kind that's on your calculator. Right? And you go to your calculator and punch the numbers in, and this is 165. There are 165 different ways. Okay, 25. An urn contains 12 balls, identical in every respect except color. There are 3 red balls, 7 green balls, and 2 blue balls. You draw 2 balls from the urn, but replace the first one before drawing the second. Find the probability the second ball is green if the first ball is red. Okay. You don't want to go for the conditional probability formula on this thing. It's actually too easy for that. You just want to think your way through it. If you draw a ball, no matter what color it is, and you return it to the urn before you draw the second ball, then nothing has changed from when you drew the first one. Right? When you go to draw the second ball, there are 7 green balls in the urn. There are 12 balls altogether, so the probability you draw a green ball on the second draw, no matter what you drew on the first, is 7 out of 12. Okay, number 26. Exactly the same setup as the previous one, except that this time you do not replace the first ball before drawing out the second. Again, you don't need a formula here. What you need to do is just think carefully. If there are 12 balls in the urn and 7 of them are green, and you reach in and you draw out a red ball, right, the situation is that you have 7 green balls in the urn and 11 balls altogether, so the probability you draw a ball out on a green ball out on the second draw is just 7 out of 11. Okay. Here's the last one. Janice surveyed randomly chosen students about whether they preferred cats or dogs as pets and found the following. Right, and there it is laid out. Who prefers cats and dogs, whether they're male or female. First, what is the sample space of this experiment? All right. When you have an experiment and the results are given in this kind of 2x2 contingency table form, you write the sample space this way. Men and cats, men and dogs, right? Women and cats, women and dogs. This is the way it's always written when it comes from a contingency table like this. All right. If one of the people interviewed is selected at random, then there are some questions. What is the probability that the person prefers cats? Well, this is easy. There are 71 people who preferred cats out of a total of 140 altogether. So you would say the probability is 71 over 140. Okay. If the person is female, what is the probability that she prefers cats? Well, once you know the person is female, you're really down to that middle line right there. The line with only women on it. Right? You have reduced the sample space to those 70 people. Right? If the person is female, if the person is in this row, what is the probability that she prefers cats? Well, there are 70 people in that row, of whom 34 prefer cats, and so the probability is just 34 over 70. What is the probability that the person is male if it is known that he or she prefers cats? Okay, if you prefer cats, then you're in this column right here. Again, we've reduced the sample space, the anyone who prefers dogs is out. We already know that this person prefers cats. Given that, what is the probability that the person is male? Well, in this column of the 71 people who preferred cats, 37 are male, and so the probability, you would say, is 37 over 71. Okay, that's the practice test.